Recording is rolling. It is Tuesday, September 20th. Here's our agenda for today and what we're looking at next few days. So, yeah, start here. Top scientist for projectile motion. There you go. So you guys did really awesome on that projectile motion quiz. So, yeah, you guys up there, you did really good. Got some owls, you did really, really good. So, definitely good job there. This is one of the harder topics for students in general, like throughout the entire year in physics, right? Because of all some complexity, right? You got to keep track of two different dimensions, and then see, one axis will affect the other. See what else we got going on here? Oh, this mystery cup. All right, so yes, you guys, who figured this out? Yeah, how's this work?
Does the straw go up past the hole up to about the middle point and then it goes back down? So when it like starts emptying, it siphons out because
Aha! Jackson got it. Jackson got it. All right. Did anybody else figure that out too? Right. Yeah, so we draw a cross section and then walk you guys through the story. Right. So it's like straw hole, straw hole. Right. Remember, the story is you fill it halfway with water stays in the cup. You fill it all the way to the brim, and the entire thing drains. The question what's going on. And so Jackson's saying, well, what's going on is that the straw goes up the side of the cup just like this. Okay. And then yeah, let's walk through the story bit by bit, right? You guys see why this works. So you fill it halfway with water, say back here, right? And yeah, some water will go into the straw, but only up to that point, right? But it'll stay in, right? So no problem. It just functions like a normal cup. Okay? Then you fill it to the brim, and doesn't it flood the whole straw? And then so water starts leaking out, right? But then, at some point, the water level is going to go back to the original level where it was fine before, but now there's some kind of state change, right? Now the entire straw is flooded, right? Including this bit here. And then here's where the siphon effect kicks in, right? You get, and then it all gets siphoned out. So you guys know how like water wants to flow downhill or reach lowest point. Well, lowest point, the system's like this point down here. And we got like one continuous system. Now, one other thing to make this work is that the water can't like break in half here and like half the mass falls to the left and half falls to the right, and there opens up a vacuum, right? Or actually, could it? Like, what if there was no atmosphere? Now, one thing, do you guys know what water does at room temperature in a vacuum? Starts with a B. Is it oil? Boil. So two things make water boil. One is higher temperature, the other is low pressure. Okay, but let's get past that. Let's suppose that there was a situation, maybe like a low temperature situation or some other kind of liquid, okay, where you could have this in a vacuum. Okay. Well, at that point, what would happen with the straw is that this actually would break this mass would, and then the siphon effect would never work. Okay. You could actually open up a vacuum here. Okay. But the fact that we're in a giant atmosphere, or giant pressure. Okay. Speaking of which, do you guys actually know one atmosphere of pressure, 1 ATM, that's 1 atmosphere of pressure. There's different ways to quantify that. Do you guys know a different way to quantify that? Pascals? Yeah, how many pascals is that equal to? It's about 101,000 some pascals. Right? What is a pascal? So 101,000 Newton per square meter. Okay. Now 1 Newton, here's 100 grams. This has a gravity force pulling down on it of about 1 Newton. It's like 0.98 newtons. You pretty much call it 1 Newton. Okay. You guys see the floor tiles down there? So here's a meter stick. Put this down here. Meter stick's a little bit more than 3 tiles, right? Right. So if you rope off 3 by 3 tiles, that's pretty close to a square meter. Not exactly, but pretty close. Right. So suppose you had like a foam cutout of like 3 by 3 tiles, right? And you stick one of these on, and so the weight of this pushing down, right? This force acting over this area, that's what pressure is, right? Force per unit area, right? Okay, that would be 1 Pascal. That would be 1 Pascal. And whoa, 100,000? Like if you took 100,000 of these and put it on foam board that's like three tiles by 3 tiles, that's the pressure that we're in. Okay, that seems like a crazy lot of pressure, doesn't it? Okay. Let me quantify this a different way. I'm going to put this in American units. I'm going to call this 14.7 PSI. Guys, what does PSI stand for? Pounds per square inch, right? Hey, pounds per square inch. Is that kind of like force per unit area? Sure is, right? Now, hold on a minute, guys. How much does a bowling ball weigh? About it would turn 15 pounds, somewhere there about, plus or minus. Okay. Oh, so is it like you have a bowling ball on every square inch of your skin right now? Is that how much pressure we're in? Yep, that's how much pressure we're in, which is a crazy amount of pressure. I mean, you would notice if it was gone, right? Like if you went to the back of his face, like, oh, where'd all the pressure go? But here's another way you quantify this. If you have a tube of water, here's what people found out way back in the day when they started inventing pumps. Okay, there could be like a town on top of say it's like a huge hill, and there'd be a lake down here. Okay? You see a lake, and here's the town. Got a bunch of little buildings, and I said, hey, what we can do is we can start pumping up this water. Okay, so this goes back a couple hundred years back. They were pumping up water, right? And then there were different towns and different like overseeing different mountain lakes while pumping up water. But they realized after a while that there was a limit to how much they could pump up. Okay? There was like a maximum height. Okay. You guys know the maximum height of water that you can pump up? H max. Okay. It's 10.3 meters if you're talking about water. Okay. Now, if you're talking about something more dense like mercury, okay, which is really dense liquid, I think it's like 76 centimeters, something like that. But water is about 10 meters, so that's about 30 something feet, right? Because you guys know if you dive deep down into a pool, you can feel the pressure going up. But if you pump up the water, say up into this pipe right here, the pressure gets less and less and less until at the very top, it like runs out of the pressure. Like so, all this atmosphere pushing down. So this 10.3. Here's another way to couch this. If you had a swimming pool that was 10.3 meters deep, and you dove all the way to the bottom of that swimming pool, you would effectively feel the pressure double. Like we're in 1 atmosphere now. At the bottom of a 10.3 meter deep pool, you would feel that pressure double. Right? So therefore, that's how much you can pump it up, and then the atmosphere runs out. Right? The way a straw operates on pressure differentials. So if you took a straw, let's say to the moon, and you were trying to like use a straw on the moon where there's no atmosphere, right? it just wouldn't work because there's no atmosphere like pushing down. Okay? And then same thing with this. Okay? Guys, suppose it turns. By the way, it's also called a greedy cup or a Pythagoras cup. Okay, if you want to Google that. Suppose they turn this to like a roadside attraction and like, hey, I got the largest Pythagoras cup ever, right? You just like out by the interstate, like, hey, look at that. It's like, how tall could you make this before it wouldn't work anymore? Well, 10.3 meters, right? If you make it any taller, then they actually would open a vacuum here, and then you would lose the side effect. All right, so fun little side quest about pressure, how pressure works. Okay. Yeah, so awesome for figuring that out. I got a warm-up projectile for you guys, and then we're going to go to the rest of the PowerPoint. And if we have more time, I want to do other stuff with you too. But okay, let's take a look at actually right before I hit that, because we're about to do a bunch of free body diagrams. Okay, tell you guys the rest of the week. So tomorrow I want to do some textbook problems with you guys because I have to get the ball rolling on those at some point. Show you guys how to solve these. We'll do as many as we can. Of course, main focus in this class too is labs. So I think the next lab I want to do with you guys is an Atwood setup. Now, let me show you guys this Atwood setup. Okay, so got some of these pulleys. They put a string through this thing. Okay, and in the ends of the string, I'm going to hook some lab weights. I'll demo this for you guys real fast, just for a moment, just so you have a mental image of what it's going to look like. But for the camera, here. Anybody watching this video, here's kind of what it's going to look like. Got a pulley, low friction, low mass itself. Okay, I'm going to hook a mass here and hook a mass here. Actually, I guess I should put the big one on top, right? Okay, put the big one up here, put the little one down here. Okay, is this thing going to probably accelerate clockwise, do you think? Okay. What if these masses were the same? What would it do? Can you just kind of hang out there in equilibrium? Okay. The more mass you put on one side relative to the other, you think it's going to accelerate faster? Huh. Okay. So this is an Atwood setup. Okay. Let me show this for you guys. Okay. So it's got a little groove in it right here. Pop the string in. Okay. And take a couple of lab weights. Hook one right here. Okay. Hook one right here. Okay. Take the heavier one to the top. Okay. Now let's watch this thing play out. Get the groove. All right, let's see. Ooh, look at that. All right, guys, that new? All right, so we're gonna do a lab related to that in a couple of days. You guys are gonna figure out what's the relationship between, say, the distribution of those lab masses, those weights, and the acceleration of the system. Say, like the acceleration of the heavy one moving down. Okay. Okay, so please plant that idea today, so you guys get a couple of days to think about that. Okay. All right. Let's do our projectile warm-up question, which I have right here. Okay. So I've got this cannon blasting this cannonball, which it says a greater diameter than the barrel, but we're going to ignore that fact. Got a physics abstraction. So launch projectile. Okay. And let's say after the initial blast attack, because of course during the blast there's a huge force on the cannonball to get it moving. But once the cannonball has left the barrel, like at this point, guys, is there any force on the cannonball from the cannon at this point? No, right? No, there might be another force, but not from the initial blast, right? That's over and done with. Okay. So what does the free body diagram look like for each of these moments, each of those snapshots? Can you draw a free body diagram on each of those cannonballs? Okay. You guys remember yesterday we did some free body diagrams. If you know what you're doing, definitely go ahead. If you're trying to remember, like, lots happened since then. Still a lot of classes, stuff. So free body diagrams, you're drawing a vector. What kind of vector? Force vector. Force vector, right? Let's see. Free body diagrams. Do you care about? But I meant to throw in one more detail here. Let's say ignore air drag. Let's just ignore air drag. Okay. We're going back to the vacuum situation. Okay. Do you care about velocity vectors? Nope. Right. Now, sometimes it's helpful to know velocity only because if there's any kind of drag force or friction force, that always resists the direction of motion. Okay. But here I'm saying just ignore that anyway. Okay. All right. All right. What you guys draw for this one right here? What forces are acting on it right here at this moment? Yeah.
Gravity.
Gravity. Yeah, so can I put a dot right in the middle to represent the center mass and draw a vector straight down? And I like to label it mg, okay? Mass times gravity field. That could represent weight, right? You could also say F sub g, right? Force due to gravity. That's a common one, because there's some gravity force pulling down. Are there any other forces on this ball? Okay, so yeah, there was maybe a moment ago, but that one's over done with, right? So it's done being blasted. Right, now it's just in motion, right? Now it's just a projectile. Are there any other forces?
No.
Nope, that's it. That's the whole thing. Okay, what about this one up here? What does that free body diagram look like?
Gravity.
Yep. Okay. Mg, the weight. Right. How about right here?
Gravity.
Yep. Mg, the weight. Mg. Okay. Yeah, remember for a projectile like that, if you ignore air drag, the only force acting on it the entire time it's in flight is just its own weight. It's mg. That's it. Okay. Now, if you did also consider air drag, we're going to look at one of those in the PowerPoint today. Okay. Do you guys think that air drag always opposes the motion? Right. Yeah. So, yeah, maybe I'll go ahead and do that edit. Why not? Okay. Scratch out the word ignore. Let's say include. Let's say there's some significant air drag. Okay. Do you guys think that the air drag would point this way? The force drag, like that, and then here probably point this way. F drag. F drag. F drag. See how it's always opposing the motion, right? The cannonball is going kind of left to right, sort of. The drag's always kind of pointing to the leftish, right? And just opposite of the motion. Guess that? Right, so some kind of drag force, resistive force will always oppose the motion. Right, guys up there? All right. I think we're ready for free body diagram, PowerPoint day 2. All right, let's switch over. Say present screen 2. All right, got this PowerPoint and let's roll this thing. All right, so that's the last one we did yesterday. It said rocket, deep space, constant velocity. What's the free body diagram? And you're looking at the answer. You guys remember that? There are no forces. See, like if that rocket had its engines blasted, like, then it would not be moving at constant velocity. It would actually be speeding up, wouldn't it? Right? So that's all you need. It's just moving because of inertia. Right? It's just going, just like the Voyager spacecraft. Okay. All right. Next one. An air hockey puck. You guys have played air hockey, right? Moving across the surface at constant velocity. So it's moving left to right. All right, did you guys say this air hockey puck has a weight pulling down? What other force? Yeah.
The levitation caused by the air hockey table.
Aha, yeah. So there's air jets pushing up, right? There's air jets pushing up. Right? That looks kind of like the normal force, right? Except in this case, just from the air jets. Okay. Are there any other forces on that puck? No, that's it. That's the whole thing. Done. Ooh, the Earth and the Moon. Now here we're going to do 2 free body diagrams, one for the Earth and one for the Moon. Okay, one for the Earth and one for the Moon. Ah, yeah, so they're orbiting, right? Or well, they're yeah, moons are orbiting the Earth. I guess technically what's going on is that they're both revolving around the very center between the two, but yeah, you can basically say that the moon's orbiting the Earth. Okay. So we're kind of stretched into future content, sort of, because we haven't talked about orbital paths really, but what if you guys can get this anyway? There's a few challenge free body diagrams that we're gonna look ahead a few weeks. This is one of them. Do you guys think that the moon is pulling on the Earth?
Yes, to an extent.
Yeah. And do you think the Earth is pulling on the moon? Okay. Now, which of those forces is bigger, the Earth pulling the moon or the moon pulling the Earth? For every force, object A and object B, there's an equal and opposite force. Ah, is that Newton's third law of motion? Right? Forces always come in pairs. There's always equal and opposite forces. Boom. Gravitational force both ways. Exactly equal in magnitude, opposite direction. Right? Newton's third law. That's it. That's the entire thing. Right? Now, you guys mentioned something to do with orbital mechanics. Right? So it turns out if you give that moon enough sideways velocity, it's always like falling around the curvature of the Earth. Okay? That's one way to think of it. Okay. Right. Yeah, we'll calculate that someday. It's like if you know what the mass and of the planet is and how far are you away from it, like how fast you have to get going to decide to like fall around the curvature. Okay. This reminds me of a question I was going to ask you guys too. Let me switch back over here real fast because we were just looking at this, right? So let's go back to ignoring air drag again, just for a moment. Okay? Whether we do or not, okay? This cannonball has a weight. It's like the Earth is pulling this cannonball down at each of these snapshots, right? Just like if I went to the edge of a cliff and I just dropped this, it'd be pulled down by its own weight, right? Okay. But hang on a minute. I said forces always come in pairs, right? For every force, there's always an equal and opposite reactive force. Okay. So if the active force is the weight of this thing, pull straight down. What's the reaction force? See, the Earth pulls this down. It's the reaction. Oh, yeah, what you thinking?
Would it pull on the Earth?
Ah, yeah, this is pulling up on the Earth. Right? But which force is bigger?
They're equal.
They're equal. They're the same. Yeah. Yeah, the Earth is pulling. Actually, the Earth is pulling this down with about 10 newtons of force, isn't it? Do you think this is pulling up on the entire Earth with also 10 newtons of force? Yes, it is. Yes, it is. Okay. Which might make you think, well, hang on a minute. If those forces are really equal and opposite, why does the motion? Why is this accelerated about 10 meters per second squared, but the Earth like basically doesn't move? Okay. Well, that kicks back to Newton's second law of motion. Okay. So equal and opposite forces, but completely different masses result in completely different accelerations. Okay, see if you put in like 1 kilogram, so 10 newtons over 1 kilogram is 10 meters per second squared, but 10 newtons divided by the mass of the Earth, well, that's pretty much zero acceleration. You guys get that? Okay. But yeah, equal and opposite forces. All right, back to PowerPoint. Okay, we're gonna look at a few roller coaster. Yeah, we're getting into like changing direction type forces, which is a little bit future content in that, but all right. So right now, let's just say it's just sitting on the top of the hill. Okay, it's kind of like quit. It's about to die. Okay. Did you guys have that there's a weight acting down and a normal force from the tracks acting up? Right, boom, boom, right? You know what I need to mention too, because I never really make a big deal out of this, but this might end up being an AP question, is that AP looks at two different categories of forces. They look at what's called field forces versus contact forces. So gravity is considered to be a field force, right? Because you can just be like floating out in space. If you're nearby, say a planet, it's gonna like pull you like a gravitational field. But a normal force would be a contact force because you need to be like physically touching the surface. I don't know. I guess there's different contexts to think about that, but that's AP's framing of it. So tidbit to know. That could be a question someday. All right, now this roller coaster plummets down, okay, and I've given it a velocity which is going to kind of enter into this, because if it was just at rest at the bottom, it'd be the same free body diagram as before. Okay, but what if it's in motion? Okay, now if you guys are riding this roller coaster and you're at the bottom of this hill, and you're the fact that you're moving to the right, you're about to start moving upwards also, right? Because you're on this curved path. Okay, you're not going to feel like you do just sitting in your desk right now. All right, moving along this curved path, do you feel really light or really heavy? Heavy, yeah, you're going to feel super heavy. Okay. I wonder what the free body diagram looks like for that. Okay, well, now there is a downward force, but that's your weight, and is that the same as it was before? Yeah, your weight's the same, right? So Earth pulls on you the same. Okay? That's no different, right? But what about the normal force from the track? Okay. I mean, the fact that if you're moving to the right, you're overall going to end up also being forced upward. Do you think that being forced upward, okay, there must be like a net force upward, right? Well, that probably might have something to do with why you feel really heavy. You see the normal force from the track, it's going to be greater than your weight. Okay, so there actually is a net force on this roller coaster cart at that snapshot, right? Because it's in motion on a curved track, right? And the difference between those two, the net force, the normal force minus the weight, which is going to be the net force, right? That has a name, starts with the C. It's called what kind of force? Centripetal. Exactly, centripetal force. All right, centripetal force, right? You guys get that? Right. So yeah, we're looking ahead a little bit, but just planting some ideas for a couple weeks from now. What about by the time you get to the top of that track? Do you feel a little bit light or a little bit heavy? Thinking probably a little bit light, unless you're going like crazy super fast around. But yeah, if you just barely make it around, then you might even approach something that's close to weightless, right? If you just like barely get around. All right, so the gravity force on you is the same as it's been for last two slides, right? Guys, which way do you think the normal force from the track? Also down. You're saying down, right? The normal force from the track is also pushing you down, right? Right? Is that it? Is that the only two forces? That's it. Yeah. Okay. Now, if you're blindfolded, then you might think that you're being thrown upwards at that point. Okay. And sometimes that could be called a centrifugal force, but the centrifugal force doesn't exist from our inertial frame of reference. It's only an apparent force if you're in a rotating frame of reference, right? Like if you're in the in the cart blindfolded. But from our point of view, that's it. From our inertial point of view, that's to say, like, we're non-accelerating ourselves. We're just watching this from the side. Okay, those are the two forces. Okay. Here's a good one. A car brakes to a stop. Car brakes to a stop. So I've got that car moving left to right. Braking to a stop.
Ignoring air drag.
Yeah, ignore air drag. All right, so did you guys have, there's a weight of the car pulling it down, right? And there's a normal force from the road holding it up, right? And what's the other force? Yeah, friction pushing to the left. Right, there you go. That's it. That's the entire thing. Right? So even though the car is moving to the right, has a rightward velocity, as a leftward net force and therefore a leftward acceleration, right? Because velocity and acceleration are opposite directions, it's slowing down, right? Right. Now, this free body diagram right here, we're going to use to solve some problems later on, and maybe like the next couple of weeks. Okay, so I think yesterday I told you guys that this friction force compared to this normal force, if you take the ratio of those, this divided by this, you get the coefficient of friction, right? Now, I think I also mentioned briefly yesterday, there's two kinds of friction. There's static friction and kinetic friction. So static friction is if you haven't broken the initial friction yet. So you're pushed against an object that hasn't started sliding. Okay. Kinetic friction is if the two surfaces are sliding past each other. Okay. Actually, go ahead and tell you a tidbit that you may have learned to get your driver's license. I know I had to. I don't know, maybe they've changed things since then. Did you guys have to learn about anti-lock braking system? Yeah, anti-lock braking system to get your driver's license. Right. Here's the difference between kinetic friction and static friction. That's what anti-lock braking is. Okay. So turns out that static friction is always a little bit more than kinetic friction can be, right? So to break the initial friction takes more force than to keep it in motion once you've broken the initial friction, okay? So suppose you have an old car like from the 1970s before anti-lock braking, right? So you got to brake in a hurry, you slam on the brake and the car skids to a stop. Okay? Well, aren't those two surfaces sliding past each other? Which means you're actually taking advantage of what, static or kinetic friction? Kinetic, which is always a little bit less. Okay. If only you could keep contact between the tires and the road so that it wasn't sliding, right? So the old advice, I'm going back like 50 years ago, don't actually do what I'm about to say, right? But if you hop in a time machine, go back many decades ago, what you're supposed to do is actually not slam the brake, but actually pump it, right? Just gently, so that you can maintain that contact so you don't slide. Okay. But nowadays, there's a computer system in your car. That's what anti-lock braking is, that takes care of that process for you. So nowadays, you actually do go ahead and slam the brake, and the computer system will take over, right? And what it'll do is it'll actually rotate the tires forward a little bit, which seems kind of counterintuitive. Like, why would you trying to brake in a hurry? Why would you want the tires to rotate a little bit? To maintain that traction, so that you can take advantage of static friction, which will actually stop the car faster. Okay, there you go. So yeah, that idea will come back in the future, but here's the setup for it. Ooh, car goes around a curve. Let's say it's seen from behind. So we're looking at the taillights of the car. Got taillight here, taillight here. We're watching it. I think I've got making a leftward turn here. I think. Okay. All right, so this car has a weight and a normal force. Right, so it's almost a given at this point, right? Okay. Suppose the guy's making a leftward turn. Okay. Do you guys think that there's a friction force between the tires and the road? There we go. That would be forcing the car to make that turn. Okay. In fact, that friction force would be the net force, wouldn't it? Okay. And you could also call that the centripetal force. Okay. So a couple weeks from now, we'll be doing centripetal force. Say like, well, okay, how is it that you turn around a curve? What's the radius of that curvature? How fast are you going? Right. I'll have you guys do a lab where you derive that equation yourselves and then put it all together. Okay. Another way you could make the car curve around a curve is you could have the road banked. We'll probably look at that someday too, but yeah. But if the road is flat, then the friction force would allow the car to turn. Okay. Ooh, a block hanging from a spring attached to a ceiling. So let's just say it's hanging there. Right. Now, if it's hanging at rest, at rest, you guys know is an example of equilibrium. Right. Equilibrium, zero net force, zero acceleration. Not necessarily zero velocity, but if it is at rest, it's just sitting there, then that would also be a case of equilibrium. Right. You guys have the weight pulling down and a spring force pulling back, and those are equal magnitude for this. Now, they're not equal and opposite because of Newton's third law, but they're equal and opposite because of equilibrium. Right. So here, just to cover my bases here, what is the equal and opposite force of the Earth pulling down on the weight? You guys just told me a few minutes ago.
The weight pulling on the Earth?
Yeah, the weight pulling the entire Earth up. Yeah, with the exact same force, right? What is the equal and opposite force of the spring pulling the block up? Yeah, the weight pulling the spring down, right? So whenever you have an equal and opposite third law force pair, it's always like two different objects. Right? It could be the block in the Earth, could be the block in the spring that you're seeing what's pushing and pulling on each other. Right? How about a bottle rocket blasted upward through the air? And there is air drag. All right, so did you guys have this rocket has a weight pulling it down, and then there's going to be like a thrust force pushing it up, and then okay, so some kind of air drag is going to resist that, something like that. Okay. And it looks like I have a net force on that rocket. Looks like there's a net force upward because the upward one is going to beat the two going down. Okay, is that okay? So it looks like that rocket is actually accelerating. Is that? Hey, when you guys see those rockets launch, since we're on the Space Coast, see rockets launch all the time. What what do you think the thrust force is coming from? Probably the rocket fuel being blown out the bottom of the rocket, pushing it forward, right? So NASA uses like hydrogen as a fuel source. So they'll have a bunch of liquid hydrogen, which is like crazy cold, and then they'll mix it up with the oxygen and ignite it. Up it goes. The SpaceX rockets, they're using methane, which doesn't have as much thrust force, but it's like easier to work with from an engineering perspective because you don't have to keep it as cold and a couple other things. Okay. Ooh, how about a baseball flying through the air at 45 degrees to the horizontal? So I gave you guys a little velocity vector there, say set off in that direction. Right. So let's say somebody's hitting a home run. Right, this ball is like mid-flight, head towards the outfield. Let's consider air drag. Did you guys have this ball has weight pulling down? In fact, if you ignore air drag, that would be the entire story, right? But if you also consider air drag, you'd also have to say it would be like opposing the motion of the ball, just like that, right? And you know the weight's going to be the same throughout the flight. It's always just the same number down, right? But that air drag is always going to change direction, isn't it? In fact, it's going to change magnitude too, because if the ball moves a little slower, it's going to decrease the magnitude. If the ball moves a little faster, can't increase the magnitude. I think I told you guys yesterday that the air drag is proportional to the square of the speed, right? So that's get tricky mechanics there. Okay. Yeah. You guys know if you go to Denver, Colorado, it's a lot easier to hit a home run because why is it easy to hit a home run in Denver, Colorado? Yeah.
Is the altitude higher?
Yeah, it's like a mile up, really thin atmosphere. Yeah. Hardly any air drag. Hey, it's our donkey friend. So two people pulling a stubborn donkey who is not moving. So let's look at the donkey. You guys see a black dot right at the point of the donkey? Okay. If the donkey's not moving, that means we're going to put in an equilibrium, right? Equilibrium. What's that going to look like? Equilibrium donkey. All right, did you guys have, there's a tension in each of those ropes, and then the donkey is, maybe there's like a friction force between his hooves and the ground that's holding it back, something like that. Something like that, right? Sometimes they use capital T for tension, but that sometimes is also used for time period, like if something's like rotating or something. So I've been trying to switch over to doing F sub T, like force due to tension. But sometimes you'll see this in old materials. Okay. So do you guys see how the leftward component, if I break these into components, suppose like aligned, up and down and then right and left, have some like Cartesian axis system, right? You guys see how the left part and the right part are like basically canceling each other out, right? And also there's two forward components, forward, and then one backward component, friction. I try to make those cancel out too. I think it's pretty close, right? It's like 5 newtons is 5 newtons forward and then 10 newtons backwards. Ah, okay. This one's really critically important right here. In fact, I've got the poster for it right there. So the answer is right there, right? So block at rest on a ramp. Okay. All right, so I'll you guys do this one. You guys have rulers on your desk? I think some of you guys do. Or you guys have some kind of straight edge? Maybe you can take a paper, fold it, maybe use a notebook, some kind of straight edge, right? Okay. First thing we're going to do is introduce, is that showing up? Okay. You know what? I'm going to do this one by hand with you guys. Let me switch my screen over. Okay. We got ourselves an incline. Some angle. We got a block. Okay, and saying it's at rest. So, all right. So first thing we're going to do is introduce a Cartesian system that is aligned to the surface. So here's parallel to the surface. And here's perpendicular to the surface. Okay. I'm going to start tagging force vectors on here. They're either going to be aligned to that system or we're going to have to break them apart in terms of that system. Okay. Now, the motionless block is pretty well constrained to the surface. Like if it starts sliding around and it'd have to like move along this axis. Okay, guys see that? So that might be one reason it might be helpful to have this Cartesian system. Okay. Now, what's one force that's going to be for sure on this block? Gravity. Yeah, exactly. Gravity, its own weight. In fact, if you didn't have its own weight, if it was like floating around in space, then well, there wouldn't be anything else going on. So that would be very exciting. So I'm going to label this mg for the weight. Okay. What's another? Actually, you know what? Before I do anything else, let's break this into components to align it with the system. Okay. You guys see this angle right here? Suppose this is like 31 degrees. You guys think that this angle is also 31 degrees? Turns out that it is. Okay. Now I won't exactly prove that, except maybe I'll do a couple things here. Where's see if I have a protractor on the desk. Did I? Oh yeah. One of these. Thank you. Let's measure this. Let's see how close this is. Yeah, thanks so much. We got this angle is whoa. All right, just coincidentally, it looks like exactly 30 degrees. Whoa. All right. Let's see if this is pretty close to 30 degrees also. It is. It is. It's like 30 degrees. Okay. So 30 degrees going on right there. And what if you did like a bunch side by side? Let's do because you could have the flat here. Let's get four going maybe. Right. Let's do like a small angle, kind of a say like a 45-degree angle. Let's say like a crazy steep angle. Okay. We have to put a block on each one of these. this is a good thing to be able to do in your mind is like animate this, say, well, you know, what if I just like change the angle? Okay, what's gonna happen? Okay. So remember we're gonna break this into components that align with this the surface like this, right? Oops, messed up that one. Yeah. Then this guy. So if I throw in force vectors, or let's say weight vectors, mg. Okay, well that's just going to be mg, so that's not going to change. This mg. Do you guys see that angle? That angle? Look about the same angle, little skinny angle. Okay. How about like the one kind of close to 45 degrees? I mean, this could be about 45 degrees each, right? Okay. What about the crazy steep one where it's like getting pretty vertical at this point? You see like a huge angle there, it might go what 70 degrees. Does that also look about 70 degrees? You guys see that? Okay. So you guys see how those angles are always gonna match? Okay. I'm sure there's some like geometric proof you could do too. Like you step through it and take a look, see that. Okay. But long story short, that angle is always that angle. Okay. Okay. Now, once we got that, let's take this weight and align it to this coordinate system by breaking it into components. You guys are going to do components like sine and cosine. Okay. So we're going to make a right triangle. Okay. Now, so what we're about to do is just having taught this class so many years, I know this is tricky for a lot of students. So it's really good practice to actually definitely break out the roller and definitely practice a bunch of these with by hand. Okay. Build these neural connections in your mind. Okay. So this vector straight down is partly pushing, this weight is partially pushing the block into the incline. Okay. And it's partially pulling along it. Now, the one I'm about to do, you guys see how I'm holding my ruler parallel to the surface? Parallel to the surface? See, a lot of students like struggle with this, right? Making this ruler parallel to the surface. Can you guys do that? Can you guys make your ruler parallel to the surface? Okay. I've just seen so many students struggle with this over and over throughout the years. So I'm really emphasizing parallel. You guys know parallel lines, right? You guys do parallel lines? Okay. You guys see how I just made a right triangle right here, where the right angle's over here? Okay. See, I didn't do it like this. I didn't do the ruler parallel to the ground, where the right angle's over here. No. The right angle's over here. And this component is parallel to the surface. You guys see that? Right? And you guys can draw that on your own paper too, right? Right? Is that okay? Okay. Okay. And no, just for context, let's see how that would change. Okay, so one where it's exactly flat, of course, all the weight is pushing into the incline. One where it's like a few degrees, almost all the weight pushing into the incline is a little itty bitty force pulling along. Okay, guess that. Okay. The one where it's about 45 degrees, I bet about 72%, 71% is pushing into the incline, and about 71% of the weight is pulling along the incline, because sine of 45 degrees and cosine of 45 degrees are each 71%. Right? And what about the one that's like almost vertical, right? Almost vertical, like almost like you put it against the wall. You guys think that only a tiny bit of the weight, this is still in G weight, right? You think that only a tiny bit of the weight is actually pushing into the wall, or like almost wall at this point, and that most of the weight, the vast majority of the weight, is trying to get it to slide along, right? Okay, you guys see that? Okay. So I just made a bunch of little right triangles. Guess that? Right angle, boom. Right angle, boom. Right angle, boom. Is that? Right? Is that? All right. So back to our blown up one right here. Okay. All right. So let's label those two components. Notice I dashed those components. Right. Now on the actual AP exam, they'll oftentimes specify draw the vectors, not the components. Okay. So either avoid drawing the components at all, or if you really have to draw them, then make sure you dash them. Because if I made these solid lines, I would be like double representing those vectors. Okay, so here's the weight, and here's the weight again, right? So it's good to at least be able to imagine this or draw it. Okay. Okay. So what is this here? This is what times what? Mg times cosine of the angle. Right. Remember that angle's that angle. Right. And what is this right here? Yeah, mg times sine of the angle. All right. Okay, you guys remember that? Okay. Okay, now that's only one force vector, but what's another force vector on this block? Normal force. Oh, and the normal force, normal means perpendicular, you guys remember that from yesterday? Isn't it gonna be perpendicular to the surface, like it's pushing out this way? Okay. You guys want to take a wild guess what the magnitude of this normal force is? Yeah, same as mg cosine theta. Same as mg cosine theta, right? So the normal force, F sub n, is equivalent in magnitude to mg cosine theta, right? Now, that might change if you did something crazy tricky, like if you put a rope on this block and you pull at some weird angle, okay, then it goes out the window. But for like over 90% of the cases, maybe every case that you guys are ever going to see in this class, these two will be equal in magnitude, okay? Because yeah, block's just like either sitting at rest or sliding along the surface. Okay. Okay. Now, if I just stop right there, actually, this looks a lot like your guys' car and ramp lab. Right, put little wheels on this block, and it's zoom, and that would accelerate down the incline. Right. In fact, the net force would be mg sine theta, wouldn't it? Right, mg sine theta would be the net force. And if you take that force and divide by the mass, you get the acceleration, which is g sine theta. Ah, all right. Guys remember that? You guys had accelerating cars. They were accelerating kind of slowly, but they were right. But if this block is at rest, like the PowerPoint slide said, then I still need one more force, which is the friction force, right? So let's throw that right here. And how long do I have to make this friction force? mg sine theta. It has to balance this one. Ah, you guys see that? This force due to friction has to be equal to mg sine theta. Okay. Now, do you guys think, suppose you had a changing angle. Suppose you like put this lab weight on your desk and then tilt your desk up. Right. And for a while, it just sticks to the surface of the desk. Do you think that as this mg sine theta increases, because the angle is increasing, that this friction force is automatically going to respond and get bigger, bigger, bigger? Right. Up to some point, and at some point, this is going to start slipping. Right. This is going to be a lab we'll have to do. I think next week. I think we're going to run out of time this week. Right, but next week. Right. Do you guys think that you could solve for the coefficient of static friction by knowing the angle that breaks that? Ooh, like there would be enough information embedded in there. You think about it really deeply, right? Maybe do a bunch of algebra. Right? Or how about this? Guys, could this block right here be moving down at constant velocity? That would be pretty much the same free body diagram, wouldn't it? Because constant velocity is still equilibrium, right? Either at rest or constant velocity. Those are both equilibrium, right? Zero net force, zero acceleration, right? But in that case, that would be kinetic friction, wouldn't it? If this is sliding down at constant velocity. All right. Well, not to be a cost point. So I will see you guys tomorrow. You guys have a great rest of your day.